very quick, we're going to return to this theme later on, and we're actually going to do a bit more on these. I'm not sure the proper pronunciation is hyperbolics, right? So I'm going to speak to some hyperbolics.
Oh, no.
This is what these are, cosh and shine, or shortened to CH. You've got various ways. As I say, I'm going to return to this and I'll give you a handout with all the different kinds of curves. You're all familiar with one kind of curve, a radius. And if you've got a radius and you spin it round, you've got a radius like that. That's one kind of curve, and then you're probably aware there's one called an ellipse, where the radius changes as you go around and then it changes back again, and you get that shape. Whoops, that's a terrible. You get basically, you would get, if I could draw, you get an oval shape. Okay, an ellipse, where you've got two radiuses basically, a bigger radius and a smaller radius if you're working from the centre, which varies as you go around. And you can do these with a bit of, you might have seen it where you do it with a bit of string, and the string as you draw it around, if you've ever seen that. If you haven't got a clue what, you have two focal points actually. I'm going off the subject slightly, but that's another kind of curving mechanism. There's another one called the parabolic, okay, which you're all familiar with, even if you're not, because you all use mobile phones, you might have satellite TV. That dish that receives the signal for you is a parabolic dish. So it's a certain shape like that, a defined radius or curve, shall we say, and then you've got an antenna that collects the signal. So when the signals hit this, they're all aimed towards one focal point. So wherever they hit it, they bounce off at its equal angle and hit this one focal point. So it's a way of amplifying the signal, catch more signal basically. So that's how your satellite dish works. So that's a parabolic curve. The last one in the puzzle is the hyperbolic, and that's this one. And this comes from, for a long time, historically, they thought that the parabolic and the hyperbolic were the same shape. Okay, and they're not. And it comes from, if you've got, say, for example, a chain hanging between 2 points, it's the shape it takes. Now, if I slacken that down and bring the points closer together, or put more chain, it ends up being more curved. Like that, and so on. Now I can zoom in onto that and I'll end up getting back to this shape, that bit there. If I zoom into that, would be that shape there. So defining how much you zoom in defines how tight the curve is. So the curve is continually changing. Okay, so that's it comes from, the term chain is relevant because if you, catenary is the term, I think that's Latin for chain, catenary, and it comes from that hanging of a chain and that shape it makes. Instead, they used to think it was parabolic in its shape, but they later on discovered it wasn't. It's its own shape, and it's a natural curving thing with anything that hangs, basically. If there's enough mass to pull it down, they don't other things affect it. So that's where it comes from. And as I say, we will look at that again later on another subject. But that's the background. Now, the maths of it is this. So the shine, this one, is actually, get this the right way around, which is the plus and minus. So this one is, the shine is our old friend Euler's number to the power of x plus e to the minus x, all divided by 2. And the cosh one, so that's your x in there, your variable x, can be defined like this, and that's a minus. Have I got that the wrong way around? I think I've got that the wrong way around. No, yeah, I've got it the wrong way around, sorry. This is the other way. That's a minus. This is a plus. I'm just going to double check myself there. Yeah, the cosh is a plus, the shine is a minus. Okay, like that. on your calculator, luckily for you, you don't have to do this every time you want to solve it, because in your calculator you've got a button and it says hip. On the Casios it says hip, and if you press that, then you get a selection, various of about 6 numbers or so, 1, 2, 3, 4, 5, 6, and I think number 2 gives you the cosh, I think. Number 1's the shine. And all you would do is, you put, in our chain, our hanging chain, X represents the distance from the centre, and it'll tell you how high it's travelled up in relation to X. It's like your sine wave. Your sine wave's got a default waveform, but you can change that by multiplying it to make the frequency faster, or you can multiply the amplitude to make the amplitude bigger. And the same thing applies to this. So this number here, for example, is going to change the amplitude, and anything in this X, like divided by 2 or something, is going to change the zooming in point. How you zoom in changes this X. You know, times it by 2, you move it, just like you do with changing the frequency on the sine wave. So it's like that. I'm probably going into it more than I intended to, but that's a bit of background for you. So anyway, because you've got that button on your calculator, the HYP, the hip, so hyperbolic as obviously short for, if that's the right way to say it, then you don't need to put all this stuff in. Sorry, that's badly written. That should be over there. Okay. You don't need to do all that. You can do it that way, the long way, but you don't need to, because you've got a button on your calculator that does all that for you quickly. Not quite relevant to what we're going to do today. All that. What we're going to do is solve this. So the method is to actually use those identities and substitute them into these, and then manipulate them and get we're heading towards this by our quadratic formula again to get two values. Okay, so let's have a look. So so if I substitute those in, I'm going to have 1.4, and then substituting for that, I'm going to have e to the x plus e to the minus x divided by 2 plus 3.2 e to the x, and this time minus e to the minus x divided by 2 equals 4.3. Obviously for the quadratic we're going to have to bring this 4.3 to the left hand side of the formula, so it equals 0, but we'll get to that. You can do it now or do it later, it makes no difference. We're going to do it later. Right, so next thing I'm going to do is I'm going to get rid of this 2 by dividing out into this. So divide 1.4 by 2, so I'm taking it out of the bracket and dividing. So I'm then going to get 0.7 e to the x plus e to the minus x plus, and then obviously that one is going to be 1.6 e to the x minus e to the minus x equals 4.3. So far nothing unusual has happened. In fact, nothing unusual is going to happen actually on this. Then I multiply out my brackets.
So this one, where is 0.7?
The 0.7 is 1.4 divided by that 2. Taking the 2 outside the brackets and divided it. So we're simplifying. Yeah, so 3.2 divided by 2 gives me 1.6, and so on. Right, if I multiply out the brackets now, multiply that 0.7 into here, then into here, and that 1.6 into there, and there, I'm going to get this. I'm going to get 0.7, whoops, don't need a bracket anymore.
Oh, Kevin, you've lost me there.
Are you okay up to this point?
No.
Right, this was, are you okay up to this point?
Yeah, I've done that.
Right.
Where have you got 0.7 from?
I've got rid of divided the 2 out. I've taken it outside the bracket and divided the 1.4 by the 2.
Right, okay.
So
3.2 divided by 2 as well.
Yeah, right.
and exactly, yeah. And now I'm going to multiply out my bracket. So I'm going to take this 0.7, multiply it into that bracket. I'm going to take that 1.6 and multiply that into there. So I'm going to get e to the x plus, whoops, I'm too fast for myself, 0.7 e to the minus x plus 1.6 e to the x minus 1.6 e minus x equals 4.3. Then, what would I do next? I multiply it out with brackets. There's certain steps you always end up taking with these things in any algebraic situation. I've got e to the x, e to the minus x, e to the x.
Add them together.
Add them together, yeah. Add the right terms together. So if I add that to that, add that to that, which is going to be a minus sign, I'm going to get 2.3. I trust me maths that much, I'm going to just take it off here. 0.9 to minus sign e to the minus x, so that's those like terms added, equals 4.3. It's certainly getting simpler anyway, if nothing else. Right, now for the freaky stuff. I'm going to multiply through by e to the x. Remember, with a formula equation, as long as you do the same thing to where the left and right hand side, it stays balanced. Like your scales, if you add something on the left and add it to the right, it stays balanced. So I'm going to multiply through by e to the x, because I can, I'm allowed, but it's going to simplify things for us. So if I multiply through with that, I'm going to get this 2.3 e to the x, so that's going to be squared basically. There's various ways of looking at it, but it's that. Minus 0.9 without an e to the x. You see what's happened there? I've got e to the x minus x, and I've times it by e to the x. So I add them two x's together, I get 0, don't I? Which makes it 1. That minus that makes it be 0, so it equals e to the 0, which equals 1. So that's become 1 times 0.9.
Yeah.
You all got that?
Yeah.
So that one's become just 0.9, and this is then going to be, have you got that? Because I'm going to rub that off now.
Say it one more time.
Yeah, so I've got e to the minus x there, I've times it multiplied by e to the x. So with your laws of indices, you add the indices to get the powers together. So minus x plus x
0
is 0. So e to the 0, anything to the power 0 is 1. So I've got 1 there, so I've got 1 times that. You out with that?
Can you just explain to us how you got up 2.3 and 0.9 again?
Sorry?
You got 2.3 and 0.9, I think I lost you then.
Right, I'm multiplying every term by that. Okay, multiply through by that. So that becomes squared, because it's e to the x, or e to the x times e to the x is squared. There's various ways of writing that. I could bring the 2 down and etc. But that anyway will do. That's probably the simplest, straightforward. When I multiply this by e to the x, because you add together the powers, the indices, they cancel out. Minus x plus x gives you x to the equals 0. So then I've got e to the 0, and anything at the power 0 is 1. So I end up with that term there. And then this finally, am I okay to rub that off now?
Yeah.
So now I'm going to get, will equal, multiplying this one by e to the x will just give me that. If I then rearrange it by bringing this to the left hand side, that's going to be my single x value, isn't it? Going to be my double one. I'm going to get this 2.3 e to the x. I'm going to bring that into there. It's the same answer. Bring this over, it's going to be minus 4.3 e to the x and minus 0.9 equals 0 now. So I'm now ready for my quadratic. Okay. You still with me? Everybody with me? We'll do another one of these in a bit.
So listen, I just forgot How did you get 2.3 and 1.9?
From when I brought my like terms together. So they had e to the x and they've got e to the x. That's 1.6 and that's 0.7. So I've added them together.
Or she... Okay.
That's 2.3.
Yeah, so that's the 2.3. And the same thing goes for this. I ended up having that and taking away from it 1.6, which left me 0.9. So I reached for my little app again, my little formula on my phone for solving quadratics, or you can do it all in your calculator and risk getting the wrong answer. Okay, the answers you get for this are e to the x. I'm going to rub that off because I need the space. You know that formula. So I've now got e to the x1 and e to the x2 equals negative 0.18999, 3 nines, and this one is
Why is it negative?
it's just one of the answers that's come out from our quadratic.
Oh, right.
It's just a solution.
Got it.
It's significant though, that it's a negative. So I'll explain that in a minute. So this one is 2.06. So like when we did the sine one, it's not actually the answer to x, it's the answer of e to the x. So we need to find the opposite. What's the opposite to Euler's number, e? So this answer here is actually 2.718, 2818 or whatever, to that x value equals that number, but we want that x value. So I've got to work backwards to find out what that x is. So the opposite to Euler's number is a log, isn't it? Natural logs. So that's simple on your calculator. Except that x there would be, so for example, 2.06. So this is going to give me the value for x2, basically. And that does give me an answer. Right, what happens when I put this one in my calculator and try doing a log of this one? If I try to do x to the 1 is natural log of minus 0.189, etc., etc. What would you get if you put that in your calculator? Try it. See what happens.
Do you be an error or something?
Yeah, it does. Gives you an error. So,
Yeah, error. Let's change it to radians.
it's not that at all, no, it's nothing to do with that. It's to do with the fact that if you plot logs, you can't have a minus answer. If you plot a log, it looks like this. And this is your 0 x value. And it goes down, gets closer and closer and closer. You remember this now, it's coming back into it. You get closer and closer, it never touches 0. So you're not allowed a negative answer. You're not allowed 0 either. You can't have log 0 either. All logs are the same, not just natural logs, any base log. So that's not allowed. So that value's, cross it out. Well, don't cross it out, but right, it's not allowed, not permitted. So there's only one. This is what I was saying earlier. You might get 2 answers from a quadratic formula, but only one of them might be valid, and the only valid one is this one. So if somebody wants to tell me what that one is, that's our only answer. So if somebody number crunches that for me, puts that in the calculator. Natural log 2.06.
0.722.
0.722. Just bear with me around. Just check it. Yeah, I've got 2, 3. Yeah.